post, for one class I already post. So for another class I will post the answers soon. So in the answers, actually I wrote for those relatively hard questions, I wrote the details already. So for some of the questions, for those questions, I may not go through all the details, because the details already in the answers file. And here I mainly explain a few questions so that I saw many common problems. All right, so let's start. Question number 5. The answer is A. Because here, internal nodes that do not have any right child. Internal. So first we know internal nodes, it must have at least a child node, right? At least a child node. Then that node can be called an internal node. But here, this R will represent the number of internal nodes that do not have the right child. Left child, yes, but no right child. So that's a special property. All right. So here we need to make some discussion on the number of nodes and total number of nodes, even and odd. These two cases, we need to do some discussion. For even, so when n even, so we can draw a diagram like this. Even. So here, let me just draw, simple diagram. All right. Like this. Even, right? Here, 7 plus 3, 10, even. All right. For odd, similarly, odd, I draw odd like this. Even, you can see R equals 1, right? So look at this part. R equals 1. The node with the internal node without right child node, that number only 1. For odd, R equals 0. Only these two cases, R equals 0 or 1, for even, odd. So A is correct. If for B, B partially correct, right? Sometimes, here, for B, you can say only when N is even, it's correct. So partially correct. If some students select B, I give partial credit, 2 points. Take away 2 points. But C greater or equal to 1, it's worse than B, right? Also, you can treat as partial correct, but worse than B. So I will take 3 points. All right? So that's question number 5. Question number 6. A few students missed this one. You need to identify that property, complete binary tree. Complete binary tree, we know, n must be 2 to the k minus 1. 2 to the k minus 1. And here, this number equals 2 to the 11 minus 1. So for other numbers, you don't have this property. But a few students, they didn't see this property, so they picked a random number. Yeah. Number 7. Yeah. Number 7. The correct answer is C. A few students select A or B, and then here, yeah, there is one property. Yeah, I talk about it in class, and I wrote something. A formula, approximate formula on the notes. Yeah. So when I discuss, so you can go to the binary search, module 4, part B. Yeah. So you go to look at that, module 4, part B. Okay. Yeah. At that place, I give you the a formula. The worst case, W minus average case. Yeah, we know it's positive, right? Yeah. But also this side, I give you less than 1. The difference is less than 1. Yeah. So A is very close to W. Very close to W, right? Yeah. So here, if we draw a simple diagram, okay, the number of comparisons we use for the binary search. B, best case B, we know equals 1, right? Yeah. The worst case W equals, we have a formula, okay? 1 plus log base 2 of n, floor function. Yeah, that's the worst case. Then the middle point, this middle point, B plus W over 2, but we know this average case A is very close to the worst case. So you can see it should be at the right-hand side of this B plus W parenthesis over 2, so it should be greater than that middle number. That number, okay? So it's C. Yeah, to see in this way. Okay? Yeah. All right. Next question. Number 10. Yeah. Most of the students I saw, so they plug in. Because the golden ratio, approximate number, so you can plug in. Although you can do that, yeah. The answer is C. Yeah. Some students, when they did the calculation, they still select, very likely they select A. Yeah, but it's not A. Yeah, but here I like you to apply the golden ratio, 2 properties for the golden ratio. Yeah, here let me show you quickly. Yeah. All right. The first property, square, we write it in this way. And we know the property phi squared equals 1 plus phi, and 1 equals phi squared minus phi. 2 properties. Okay? All right. Then we want to bring down the degree as much as we can. Okay, as much as we can. All right? Yeah. So here, bring down the degree. Phi squared, replace it by 1 plus phi squared plus phi times 1 plus phi. Okay? Yeah. So here I need to use a little more space down here. So 1 plus 2 phi plus phi squared plus phi plus phi squared. Okay? Yeah. Combine the terms. Yeah. 1 plus 3 phi plus 2 phi squared. Okay? 2 phi squared, yeah, let me jump one more step. Can I replace 2 phi squared by 1 plus phi by the first property of golden ratio? Yes. Then combine the terms. yeah, 3 plus 5 feet. Yeah. That's option C. Okay? Yeah. I'd like you to use this way. Yeah, this way. Yeah. 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 All right, so that's number 10. Number 11, yeah, so now you can see number 11, power of phi, we want to see if any power of phi, yeah, for positive n can be represented in the form of a phi plus b with ab integers. Answer is yes. How to see it? Yeah, some students can understand, can imagine the process to do that. Yeah, because so phi to the n equals phi squared times phi to the n minus 2, right? Yeah. And the phi squared you can write as 1 plus phi times phi to the n minus 2, right? Yeah. So phi n minus 2 times phi n minus 1. All right? Yeah. So here you bring down the degree number. Yeah. Can you keep doing the split like this? Keep bring down, right? Keep bring down. Yeah. And when you get to the bottom, you will get this form. Because after that you cannot bring down anymore, right? Yeah. So whenever you can find a term with degree greater or equal to 2, then you can use the first property of the golden ratio to bring it down in this way. Replace phi squared by 1 plus phi to bring it down. Yeah. The last step, that is, because in this representation, a phi plus b, there is no phi squared term. So you cannot bring it down anymore. You have to stop. That's the destination we need for this question. Yeah. So the answer is yes. Yeah. Okay? Yeah, so you can see in this way. All right. Number 14, quite a few students missed number 14. The answer is A. Yeah. And here the relationship is very simple. Okay? Internal node I equals flow function n over 2, flow function. And L leave ceiling function. Okay? Yeah, ceiling function, the representation. And then we know the floor function is always less than or equal to the ceiling function, right? Yeah. So that's option A. Okay? Yeah. Small number of students, pick C. Yeah, I think. Yeah. Yeah. All right, so that's an easy question. Yeah. Number 16, I gave the hint in class. Yeah. So it's about we need to use mathematical induction. Yeah. But many students, they couldn't get it. Yeah. So even I showed the critical formula, mathematical induction formula. Yeah, but those students, they couldn't see it. Okay? Yeah. To solve, yeah, because here we consider positive integer. Actually, when n, we can include n equals 0 case. Greater or equal to 0 is correct. Because when n equals 0, it is 1 plus 1 equals 2. It's also a positive integer. Yeah. But n equals 1, phi squared plus 1 over phi squared. Can you see this is an integer? Yeah. So let's take a look. Phi squared plus 1, 1. Let's apply the property, the first property here. 1, yeah, 1. Phi squared minus phi. How about that? We'll replace 1 by phi squared minus phi over phi squared. Okay, so that is 1 plus phi squared minus 1 over phi, right? Yeah, okay, all right. Then let's do some more formula transformation. Phi squared, we know 1 plus phi, right? Yeah. 1, we know phi squared minus phi, right? Over phi. Okay? Yeah. So let's simplify it. 2 plus phi minus phi minus 1. Okay? Yeah. After cancellation, we get 3. Yeah. So that's correct. Okay? Yeah. So we verify when n equals 0, correct. When n equals 1, correct. These two base cases, correct. Yeah. Then we can make mathematical induction assumption. Okay. So induction assumption. Okay. Yeah. What's that? So that means when yeah, so how to write that? Okay, yeah, so let's write 0 less than or equal to k less than or equal to n. Yeah, for this range we have phi 2k plus 2k right, 2k is positive integer. That's the induction assumption. Okay? Yeah. All right. Then, next, remember I give you one critical property in the hint video. So what's that? That is, so here I use this expression as a sub 2n. Okay? All right. That critical property, it is a 2n plus 2 equals a2 times a2n minus a2n minus 2. Okay? All right. Now by induction assumption. Yeah. All right. So a2 something, but when k, so here, what's the k? This case, k equals n. This case, k equals n minus 1, right? Yeah, 2 times k. Remember, 2 times k. Yeah. All right. So here, k equals n in the range, right? K equals n minus 1 also in the range. Okay? That means we can apply induction assumption and give us integer, right? They're both integers. So the whole thing must be an integer. Here we do not say positive or negative. We just say integers. Because here there is subtraction. We don't know. After the subtraction, it is still positive. But from the original expression here, because Ph's even number of exponent must be positive, right? Plus 1 over a positive number, also positive. So this gives us, it must be positive. So positive integer, because we have positive. Then we get a positive integer. Okay? So by mathematical induction, we can show it is positive integer. Then, based on the conclusion for the mathematical induction, the whole statement must be correct. The whole statement. Because we follow the standard 3 steps, 1, 2, 3. The first step, verify the base cases. Here we verify 2 base cases, n equals 0, n equals 1. Second, induction assumption. Step 2, induction assumption. Okay. Step 3, we expand the range. So this is the range in the induction assumption. But in our step 3, we expand it. We expand the range to n plus 1. Here, this case is k equals n plus 1. That's out of the previous range. We expand it. We extend it. We enlarge the range. So we can use this property to enlarge the range. And we can keep enlarging. Okay? Keep enlarging so we can cover all the integers, all the positive integers. Okay? So the whole process. So if you can follow, that's the way we apply mathematical induction. Okay, so I hope you can follow, you can understand. So here I give you 2 exercise questions to practice mathematical induction. Okay, all right, So let's move to other questions. The questions I didn't circle, that means you can go to the answer file to see the solution easily. Okay, because number 17, you just apply the formula. Many students, so here we have the formula and this formula. Okay, or another formula, equivalent plus 1. Okay, both formula give us the answer 9. Many students give me 8. 8. So you need to pay attention to the little details in these 2 formulas. So after we learn the binary search, you need to know this kind of details. Okay, all right. Number 18, we did one in class for n equals 12, right? N equals 12. All right. So some students followed that example and are doing well. But many other students, they didn't follow that example. And some students, so they find some formula. So this case, for worst case, Yeah, so they can find some formula on web. Yeah, but one student, I saw the formula correct. Yeah, but another student, the formula not correct. Yeah, and here I do not talk about that formula. I want you to practice. How do we do the merge sort? Okay, yeah, so the answer is 25. Yeah, yeah. Many students give me 23. Yeah, and also some students apply that formula. That's not good. And many students plug in and don't do it. Yeah, don't do it, because actually this is not a formula, right? You know, this is not exact formula. This is asymptotic notation. Yeah, merge sort asymptotic notation. Look at the symbol here. Yeah, so you cannot use asymptotic notation to calculate exact number. Here we need exact number. Yeah. But many students plug in n log n, you know, give me 33 something, point something. So then round it up, 34. That's not correct, okay? Because it's asymptotic notation. Yeah. The correct answer, 25, you can see different from that asymptotic notation based formula. Okay? Yeah. So that's a big mistake. Yeah. Number 19, the answer 29, yeah, you can see, add up these two numbers, because we use the best case here. The best case formula is minimum of m and n. Yeah. Yeah. Here there are three possible solutions you can try. Yeah, three possible solutions. Yeah. So here, if you try, you merge the first array 25, because this would gives you take the minimum. Okay, you take the minimum. All right, minimum. So number of comparisons 12, but you will get 37 element array. Yeah, so here we use this notation. Okay, yeah. So these two parts both useful. Yeah, because our next merge would be 17 and 37. We need to use the number of elements in the first merge step. All right, yeah. So you get 17 and 54. Yeah. And many students give me 54 as the answer. Yeah. So that's not correct. Okay? Yeah. Add up these two, 12 plus 17 equals 29. Okay? Yeah. So that's the way we merge these three arrays for the best case. Yeah. For the worst case, then another big problem. Here I like to talk about another big problem. Also, three possible ways. Yeah, here the question is another one. First, the formula we use, m plus n minus 1. Okay, yeah. So those students know. So most students, they know the formula and they know how to work on those three cases. Here I just talk about result. The first case, so they merge in certain order, so they will get 91 comparisons. Okay, yeah. The second case, after they merge in certain way, they will get 103 comparisons. The third way, they get get 115 comparisons. Yeah, so that all those students, they got correct. Thus, but when they make conclusion, they select 115. Yeah, most of students, they select 115 because, so now I understand why they select 115, because they thought it is the worst case, right? Because you're asking about the worst case. So they give me this as the worst case solution. Yeah. Here, one big mistake is, yeah, all right. Correct answer, this is the correct answer. 91, correct answer, okay? All right. So let me clarify. All these three solutions, all three, yeah, so all three solutions are for the worst case. Yeah. Because all three solutions, we apply this worst case formula, right? You didn't apply the best case formula, right? You didn't apply the other case formula. You apply worst case formula, yeah. For different merge orders, right? Yeah, because the difference is at the merge order. It's not the best case, worst case. The difference is at the merge order. Different orders would result in different solutions, but all for worst case under that particular order, okay? Under that particular order, okay? Yeah, but our goal here, when you have several solutions, you want to find the best solution, not worst solution, okay? Because you always want to find the best solution, right? People always want to find the best solution, okay? Now, here, because they are all for the worst case, and 91 is the best. Smallest number of comparisons is the best. So we want to have the best solution. Still, it is for worst case. It's not for best case. Yeah. Okay? Yeah. 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 But under some specific order, this 91, there is a specific order. Yeah. And we know in class I mentioned that greedy algorithm. This corresponds to, yeah, so related to the greedy algorithm. Okay, yeah. So greedy, how greedy? So we merge these two first, right? Yeah, merge these two. Yeah, so we get a, the first time. Yeah, so you get 29, right? 29 comparisons. But after that, you get 30 elements. Then you merge these two, 62, okay? 62 comparisons. 62 comparison, you plus that 29. Yeah. So you get 91, and here you apply the greedy strategy. Yeah. So every time when you select two subarrays to merge, you pick the two shortest subarray. That's the greedy strategy. Greedy strategy. So this example, you can see, we can apply the greedy strategy to get the best solution. Greedy strategy to get best solution. Yeah. Think about that. That's important, because if after this example, if you can summarize to get this result, you can greatly reduce your computing time. For example, here, let me give you, example. For example, yeah, because in this question, I give you 3 arrays. If I increase the number of arrays, okay, if I give you, 6 arrays, how about that? With sizes, with the following sizes: A, B, C, here I do not give you concrete numbers, D, E, F, okay? 6 different integer numbers for the array sizes. Definitely you don't want to exhaust all the possible merge orders, right? Yeah, so that's too much work. How can you do it? Within the limit amount of time, how can you do it? Too much work, yeah. But if you apply the greedy algorithm, here, you can find the best solution quickly. How about that? Can you see it? If you apply the greedy algorithm strategy, you can find a solution quickly, because you only need to do in one certain order. That order is given by the greedy strategy, and that one, you can get the best worst case solution. Why? Yeah, because after we discover this property, yeah, we can prove it. Yeah, we can prove. Yeah, if you want the rigorous proof, yeah, so you can get it. Yeah, but here in this class, we won't do it. Yeah, we just use the result. Yeah, it won't be too hard. Yeah, we can prove it. Yeah, still, it will prove it by mathematical induction. Okay. Yeah, we can do it by mathematical induction, but a little harder. Yeah, when we do it, a little harder. Okay, yeah, but we can do it. We can prove it. All right. Yeah. So here you can see from this example, you can understand the importance of the greedy strategy, greedy algorithm. Okay. Yeah. All right. Yeah. That's this question. Question number 21. In my solution, I put the details. Yeah. And in the hint video, I explain. Yeah. I use a simpler example to explain. For a question like this, what is the standard procedure to find a solution? Yeah. So 2 places you can get a solution information. Okay. All right. Number 22, I explained, I use a simpler example to show you the standard procedure in a hint video. Yeah. You just find a hint video. You can see it. Number 23, in the notes, we did a concrete example. Here you just use the same way. Yeah. But when I did a grading, I noticed so many students, they didn't apply our standard partition procedure correctly, so they missed a little bit. Yeah, they missed a little bit. Yeah, and I have the details in my solution file. Okay, all right. Number 24, the range, the general formula, actually number 24, number 25, we can discuss together. Yeah. So the general range for the index of a node of height h, so we have this range formula, okay, yeah, lower bound h plus 1 less than equal to index I, also lower bound h. Okay, yeah. So that's the range formula. Okay, yeah. But for question 24, h equals 1, height 1. Okay. For question 25, leaf, right? Yeah, because smallest possible in the, yeah, what is small possible minimum value? Yeah, because the minimum value must correspond to a leaf node, a leaf, yeah, and the range at the height of the range height of a leaf equals 0. Yeah. So you can use the same range formula but with different height. So height 1 and height 0, but you use the lower bound. Yeah, because we want the smallest possible index. Smallest possible index. That's the lower bound. That's the smallest possible. So the answer for number 24, h equals 1. So n over 4, floor function plus 1. H equals 0, n over 2 plus 1. Okay? Yeah. All right. So that's all the selected questions I want to explain in this video. Yeah. The remaining information, you can use my solution files, answer files. Yeah. So for the online section, I will post that file. Yeah. In-person section, I already posted. Yeah. All right. Okay. So that's it.